Here is a mind-bending fact. The energy inside a single atom can outshine hundreds of thousands of tons of TNT, and yet, that's just the starter level of nuclear physics. Today, we re-exploring a scientific rivalry so extreme that even physicists sometimes describe it as fire versus a second. Bigger fire that decides the first fire wasn't enough. This is the atom bomb versus the hydrogen bomb. Two technologies built on the same universe, yet separated by orders of magnitude in raw physical power. To understand this comparison, let's begin with the simpler one, and simpler is a very relative term because atomic physics is never truly simple. The atomic bomb, or fission bomb, releases energy by splitting heavy atomic nuclei like uranium-235 or plutonium-239. This process is called nuclear fission. When a nucleus splits, it releases three things: enormous amounts of heat, intense radiation, and free neutrons that fly out and hit nearby atoms, splitting them too. This creates a chain reaction. It's kind of like a line of dominoes, except every domino also releases more dominoes that weren't even there a second ago. And the neutrons? They move so fast that if they had driver's licenses, they'd be banned from every highway in the world. So how much energy does fission actually release? When a single atom undergoes fission, the energy released is roughly 200 million electron volts. Now, that is a very big number for something smaller than a virus. To put it in real-world terms, a typical fission bomb yields about 10 to 20 kilotons of TNT equivalent. That means one bomb has the explosive energy of 10,000 to 20,000 tons of TNT. And yet, as you are about to see, this is still considered the junior league of nuclear physics. Despite its destructive power, the fission bomb has physical limits. The chain reaction can only continue as long as the material stays together, the neutrons keep interacting, and the mass remains above a critical point. This window of opportunity exists for just microseconds. After that, the material blows itself apart, ending the reaction. This natural limit is exactly why scientists had to wonder, is there a way to unleash even more energy? And physics answered, yes, by doing the complete opposite of splitting atoms. This brings us to the hydrogen bomb, or thermonuclear bomb. It uses the power of nuclear fusion, the very same process that powers our sun. Fusion forces light nuclei, like hydrogen isotopes, to combine into heavier nuclei. This releases even greater energy than fission because the tiny difference in mass is converted directly into pure energy via Einstein's famous equation, E equals mc. And if you've ever wondered what that c² part really means, it is effectively the universe's way of saying, small mass? No problem. I'll turn it into a ridiculous amount of energy anyway. Now, fusion requires temperatures of tens of millions of degrees, conditions similar to the sun's core. So how do you create that on Earth? Well, here's the twist. A hydrogen bomb actually uses a mini fission bomb as the trigger. It's a three-stage process. Stage 1. The fission bomb detonates, creating the initial blast and a flood of high-energy X-rays. Stage 2. Those X-rays compress and heat the fusion fuel to stellar temperatures. Stage 3. Fusion ignites. This two-stage design is known as the Taylor-Ulam configuration. In a bit of scientific humor, you could say the hydrogen bomb is basically the atom bomb's bigger, angrier sibling that uses the atom bomb as its alarm clock. So just how much more energy does fusion release? On a per-reaction basis, fusion releases 3 to 4 times more energy than fission. But because fusion fuel is extremely compact and can burn with incredible speed, the total energy yield becomes far, far greater. A typical fusion bomb can yield anywhere from 1 to 20 megatons of TNT. That's the equivalent of 1 million to 20 million tons of TNT. Suddenly, the fission bomb, with its kiloton yield, starts to look like a firecracker compared to this thermonuclear storm. Let's put that scale into perspective. An atom bomb is in the range of 10 to 20 kilotons. A hydrogen bomb is in the range of 1 to 20 megatons. The difference is a factor of 100 to 1,000 times more energy. This is why hydrogen bombs are often described with phrases like planet-scale energy release, even though their design and use remain heavily restricted and tightly controlled under international treaties. To really understand this energy difference, we need to look at the binding energy curve. Heavy atoms release energy when they are split apart. That's fission. Light atoms release energy when they are combined. That's fusion. The peak of this curve is iron, which has the most stable nucleus in the universe. So fusion reactions of hydrogen move up the curve towards iron. Fission reactions of uranium move down the curve towards iron. Both processes release energy by moving towards a more stable state. They just do it from opposite ends and with vastly different magnitudes. Hydrogen, at the very start of the curve, is like a tightly compressed spring just waiting to snap into a lower energy state, and that snap releases astronomical power. When comparing the physical effects of these two technologies, three major factors stand out. First, blast pressure. Hydrogen bombs produce shock waves that can travel for dozens of kilometers. Second, thermal radiation. Fusion temperatures can reach 100 million degrees Celsius. The intense heat released can ignite anything combustible over vast distances. And third, prompt radiation. Both types release intense gamma rays and neutrons. But fusion adds another layer: extremely high-energy fast neutrons, some of the fastest particles humans are capable of generating. These neutrons are so fast that if they were athletes, physicists would be testing them for performance-enhancing cosmic rays. One of the most remarkable properties of hydrogen bombs is their scalability. Fission bombs quickly reach a maximum practical size before they become inefficient. Fusion bombs, on the other hand, can scale upward. You can add more fusion stages, and the energy release grows in a near-exponential fashion. Once again, physics reminds us, fusion is incredibly efficient, almost too efficient. Thermonuclear reactions brought scientists face-to-face with energies normally found only in stars. For the first time in human history, we understood what stellar power looks like in physical form. This discovery led to major breakthroughs in plasma physics, astrophysics, fusion research, high-energy particle studies, and radiation transport modeling. This knowledge, when applied peacefully, has helped shape the research into fusion energy reactors, which one day may supply humanity with abundant, clean power. So we can finally return to our core question: which bomb is more powerful? And here's the most shocking scientific fact of all. Despite their unimaginable power, both of these technologies operate using the exact same principle. Mass can disappear and reappear as pure energy. This is not science fiction. This is the universe revealing one of its deepest secrets. In every atom around you, in every molecule, in every breath you take, the potential for unimaginable energy exists. The real power lies not in the technology itself, but in understanding the fundamental physics that shape our entire universe. So to summarize, atom bombs use fission to split heavy atoms. Hydrogen bombs use fusion, triggered by a fission bomb, to combine light atoms. Fusion releases far more energy per reaction, and its design allows for megaton yields, making hydrogen bombs drastically stronger. The physics behind them teaches us about stars, energy, and the very building blocks of the universe. And though these technologies exist in highly restricted and controlled contexts, the science behind them continues to expand our understanding of matter, energy, and existence itself. If you want to keep exploring the strange and astonishing edges of science, where physics becomes almost unbelievable, then subscribe to CNEX. Because together, we'll keep pushing the boundaries of what we think we know. If you want to push the limits of science with us, don't forget to subscribe. Thanks for watching.